The math learning experience for measurement is called In Search of Pi. And as you can guess, we're going to be talking about circular measurement, in this case specifically circumference. The title of this math learning experience is pretty much the direct opposite of what we see on this slide. Ideally, we want students to search for pi, to discover, to investigate, and to be active-minded in their learning. But sadly, what we see here is how many students have learned and continue to learn about circumference and mathematics. I recall my own experience where the teacher told us the formula, told us what we needed to know about pi, and we did a lot of questions similar to what we see on this worksheet. The problem with this, of course, is that that's a very boring and passive way for students to learn mathematics, and as a result we have a lot of adults and young and kids walking around in our world today who don't like math and don't identify themselves as math people. So we need to change that, and it's all about the presentation, because circumference can be surprising and beautiful if it's presented properly, and students deserve to see it that way. So here we go. In this math lesson, they're going to start off by measuring objects for circumference and diameter, and they're going to use string and rulers and or flexible measuring tapes, and they're going to input their data onto this chart. So I've done that right here. I've measured 5 things, and I've got circumferences and diameters put into the table here. Now there are 4 columns, and one for each of the operations, and they're going to use their circumference and diameters with each operation, and I've done that, and here we go. Now imagine being a 12 or 13 or 14-year-old student doing this and looking at the 4 columns of operations. What do you see? Well, obviously what you see is that for the first 3 columns have no consistency. The numbers are all over the place. But what is surprising and makes students want to ask questions is what's happening in the circumference divided by diameter column. There is a fair deal of consistency. The numbers are all in the same range, and that causes them to wonder, and they want to know why. This is much better than simply being told a formula and plugging numbers in 25 to 50 times. So obviously they're not quite there yet. They see that something is up. They see that there's something significant about circumference divided by diameter. And of course, this is a good time for the teacher to ask questions like, well, what if we didn't round our numbers, and what if we used more precise instruments of measurement? Do you think maybe circumference divided by diameter would be the same number for all circles? And some students might see that that makes sense, and other students might not be able to see beyond the data they have in front of them, but that's okay, because what they have now learned is that there is something significant about dividing circumference by its diameter. Okay, and we can take that into the next stage of the lesson. And the next stage of the lesson, there are many ways that you can kind of get at pi, that you can investigate pi, and this is just one way that I'm presenting. The first stage is with this activity, this unplugged activity. The second stage is taking a look at other shapes. Now, it might seem counterintuitive that we're learning about circles by not looking at circles, but just bear with me. So what do we see here? We see a variety of regular polygons with even numbers of sides. And in each case, the perimeter of the polygon has been divided by the length of its diagonal. And what do we see here? 3 right on the nose, 3.06, 3.09. Now we know that these numbers are creeping up and approaching pi. And what we can also see is that as the number approaches pi, the figure becomes more circle-like, doesn't it? So what would happen if we had something that was very circle-like, like a 30-sided figure? Well, there it is. So we have a 30-sided figure, and when we divide its perimeter by the length of its diagonal, we get 3.14, which is not pi. It's not exactly pi, but it's an approximation. So the point here that the student should see is that as your polygon becomes closer to a circle, your perimeter divided by length of diagonal starts to converge on a certain special number that will be useful for circles. Okay, and with each step in between polygons, and this will be made clearer in the next video when I talk about the CT coding advantage, each movement between polygons, the change in this number here becomes smaller and smaller. And again, that will be clear as we get to the next video. On the other hand, what if we take a look at regular polygons with odd numbers of sides? So we have here a pentagon, and this time we're dividing by a line of symmetry, so you can just see it between A and B here. Okay, and when I take the perimeter and I divide it by the line of symmetry, I get 3.25. So this time, whereas over here, we started off less than pi and worked our way up closer toward pi. In this case, we're starting above pi. Now what happens if I make a jump to a regular polygon with a higher but still odd number of sides? Well, here we are. So now we have a 15-sided figure, regular polygon, and we're dividing the perimeter by the length of the line of symmetry, and we're down to 3.15. We were at 3.25, we're now at 3.15. So again, we're converging on pi. And once again, this figure here with more sides is more circle-like than the pentagon over here. It looks more like a circle. So this is a good way to show students that as the closer you get to a circle, the closer the quotient is to a number that you can then tell them is pi and give them all the information they need to know about it.